The last topic in thermodynamics that we're going to touch on is one of the strangest. And I would actually say it's the strangest idea in thermodynamics, and that's entropy, which we might think of as disorder. So, how do we measure disorder and why does it matter? And that's what you'll learn about today.
So our statement of the efficiency of a Carnot engine suggests that the larger the difference we can have between the incoming temperature, TH, and the outgoing temperature, or the exhaust temperature, TC, the higher our efficiency is going to be. So if we have a system that looks like this, right, we would have a higher efficiency than one that looks like this. Okay, this begins to suggest a different way of thinking about the second law, which is in terms of order and disorder. Okay, what does that mean? Well, the more we structure our energy, the more we have um, distinct differences between one area of our system and another area of the system, the more our energy is made usable. So let's look at this in an example. So imagine we have three engines, right? One with this temperature difference, one with this temperature difference, and one with an equilibrium between TH and TC. They all have the same thermal energy, right? If they're all of the same material. Um, but what are their efficiencies? Well, if we figure the efficiency of the top one, we put in TC and over TH, and we get an efficiency of about zero point 0.5. Okay, not great, but in the real world, that's actually pretty good. What happens with this middle pair of reservoirs, right? With a T hot of 500K and a TC of 400K. Well, in that case, we have an efficiency of about zero point 0.2. Uh, Significantly worse than this one, right? And if we are at equilibrium, can we produce any work at all? And the answer to that is no, right? You get 1 minus 1, and that would be 0. So this, if all of that energy that we have here is mixed together, that is, if it's disordered, um, then we don't have any potential for work. We don't have any usable energy. As energy becomes less ordered or less structured, it becomes less usable. So, what does that mean? Well, here it gets captured in the idea of entropy, which is probably one of the hardest terms to understand in all of physics. Entropy is a measurement of the disorder of a system. Um, and it's really hard to get a physical sense of what that means. You just have to sort of trust that measurement of entropy represents disorder. And we can restate the second law as the total entropy of a system either increases or remains the same. It never decreases. So disorder is always increasing in real world processes. And that means we're moving more towards equilibrium, right? Structured systems where you have, you know, much different conditions here than you do over here eventually are going to move towards equilibrium. This has a rather frightening conclusion for us, which means that the universe is destined for thermodynamic equilibrium. This is called heat death, and it means basically everything is the same in the universe. Fortunately, that's a long time away, so we don't have to worry too much about heat death. Um, but it is an interesting conclusion. Like all of the structure in the world, if it's moving towards equilibrium, then eventually there won't be very much structure left. In the short term, what it means is that we have limited efficiencies in our various thermodynamic engines. Okay, so if we want to calculate entropy, we can calculate it as this. So this is the change in heat over the temperature at which it happens. Um, the S total in a process is always going to be greater than 0. they're going to be individual parts of a process, then it might be less than zero. But the total change in a total change in S is always going to be positive. That is, we're moving more towards disorder and towards equilibrium. Okay, so let's talk about this in a practical way. How does that equation work? Well, let's imagine we have this system, and we're just going to mix it to create this system. So our thermal energy is unchanged from here to here. But let's see what happens to our entropy. So we have 10 kilograms of water at 600K and 10 kilograms of water at 300K. Um, so we have two processes here. We're going to transfer heat out of the hot water uh, to make it reach 450. And then we're going to transfer some heat into this cold water to get it up to 450K. For each of those, our Q is going to be modeled by what we learned in our section on heat transfer, right? Um, the change in energy is going to be the mass times the specific heat times the change in temperature, right? So the Q for each of these, because they're both changing by 150 degrees K, is going to be this value here, 6.3 times 10 to the 6 joules. Okay, one of these processes is going to be positive and one is going to be negative, though, right? And then to find the entropy, really you'd want to use calculus, but we're just going to use the average temperature, and that gives us a pretty good sense of the answer here. So for the heat transfer out of the water, out of the hot water that is, for that process, Q is negative, right? Because we have heat leaving this hot water. And our change in S in the hot water is this negative Q over T. And we get this entropy. Entropy is in joules over Kelvin. And then for the change in the cold water, that Q is going to be positive because we're adding heat energy. And our temperature, our average temperature is lower, right? Halfway between 300 and 450. And this is the change of entropy in the process of changing that cold water. The total change in entropy is the sum of these two, right? And our value is 4,800 joules over Kelvin. Now, what does that mean physically? That's, again, this is where entropy is very hard to understand what those units mean and um, how to imagine that as a physical process, but we don't need to worry about that too much. What we really need to know is that this number is always going to be positive, this S total. And you can just see why that is, because adding the positive change here is going to be divided by a smaller number, and the negative change is going to be divided by a larger number, because we're taking heat out of the hot system at a hot temperature, adding heat at a cooler temperature for the cold system. And so the disorder in this system increases, which we can see because we have a highly structured system here and we have a non-structured system there. Entropy has increased.